At the sun. We're going to explore what powers the sun, what it's made of, and how it affects us here on Earth. So to start, we'll get at kind of what powers the sun, and we can always think of the sun as a big burning ball of gas, which is true in some sense, but it's not burning in the sense that like a fire in your fireplace is burning, or propane on a stove, or gas on a stove is burning. It's more like a giant nuclear explosion. So for main idea, we'll say with sun's energy, right? And it's burning, but not like fire, right? It is the equivalent basically to many, many, many nuclear bombs exploding all at once. So it's powered through nuclear fusion. And each second, the sun releases the energy of 2 billion nuclear bombs. The sun releases the energy of 2 billion nuclear bombs every second. So you can imagine the sun basically being 2 billion nuclear bombs exploding every second for your entire life and much longer than that. So we're talking massive, massive, massive amounts of energy. So when we say it's burning, it's not burning like fire. It doesn't need oxygen the same way that a fire on Earth would need oxygen. So that's how it can just be that exists in outer space. All right, so the structure of the sun. All right, the sun is mostly made up of two gases. All right, and this isn't on the PowerPoint, but we're going to put it in our notes. It's made up of hydrogen and helium. All right, mostly hydrogen, but with some helium. All right, in that nuclear fusion, it's turning hydrogen into helium and releasing energy. So at the center, you have the core, which is where the nuclear reactions take place. All right, temperatures there are in the 14 to 15 million degree range, which is unbelievably hot. You have the radiative zone. All right, and here energy moves outward from the core. And then finally you have the convective zone. And here we're going to have convection currents, so we have hot gases moving in convection currents to the sun's surface. All right? All of these layers are gases, so this is a gas in the center, this is a gas here, this is a gas out here. All right? It's super, super hot, but it's still a gas in that you could, in theory, go through it, except that whatever you dropped in would be instantly incinerated. So there is that. All right, once we get to the surface is called the photosphere. This is the surface of the sun you see from Earth. All right, photo meaning light sphere. This is literally the part that you see. And then beyond that, you have the corona, which is the kind of atmosphere of the sun. All right, it's only visible during a total solar eclipse. It's not very bright, but you can see this ring around the sun. Right? These are gases leaving and streaming out from the sun's surface, and this is called the corona, so only visible during a total solar eclipse. All right, that's the structure of the sun. We're not going to go into a super large amount of detail on it. All right, features of the surface. All right, the surface has some cool stuff going on that we're going to look at quickly. The first feature we see on the sun's surface is that we have these things called sunspots. These are dark, cooler areas. All right, we don't quite know why these are here. We know that they are there. They have really strong magnetic fields on them, and again, they're kind of a mystery. They seem to come and go in cycles. We don't really know a ton about them. Next, you have what's called a prominence, which is a huge loop of gas from the surface or from the photosphere. All right, you can see this huge prominence, this huge leaping thing of gas. There's an Earth next to it for comparison. Obviously, the Earth is much farther away, but this gives you an idea that this prominence is easily 20 times the size of our planet. All right, and then a solar flare is a prominence that erupts into space, releasing charged particles. All right, these flares get shot off in a particular direction. If they get shot off at the Earth, then they can end up having a pretty big effect on our communication, on our satellites, that can knock out power lines and power systems. So we can monitor these things. We tend to have a pretty good idea of when they're coming, and we can try and at least be prepared for their impact. But there's nothing you can do to stop a solar flare. As you can see, it is way bigger than our planet, and there's nothing we could do to stop it. And the last thing we're going to look at is how the solar wind affects the Earth. So the solar wind is a stream, just a constant stream of charged particles being released by the sun. All right, you can kind of think of it like the wind on Earth being moving air. This is just a constant stream of charged particles. You wouldn't feel them hit you, but they're constantly moving away from the sun. So a solar wind is a stream of charged particles released by the sun. And when these particles hit the Earth's magnetic field, they release energy in the form of light. Magnetic field, they release energy as light, and this light is called the aurora. All right, you may have heard it called the aurora borealis. That's what it's called in the northern hemisphere, or the aurora australis in the southern hemisphere. So it's called the aurora or the northern or southern lights, depending on where you are in the world. All right, you usually only see these at the poles, because that's where the Earth's magnetic field comes down close to the surface. If you're near the equator, you can see kind of in this diagram, the magnetic field is way out here. Up near the poles, though, the magnetic field gets close to Earth, and so you get these charged particles visible from the surface. It's called aurora, or the northern, southern lights. Alright, so for those of you who had asked what was the deal with the northern lights, this is what it is. It's particles from the sun hitting the Earth's magnetic field and giving off light. Make sure you do a summary on your notes and take a look at the survey, and I will see you in class tomorrow.